Hey, everybody. Fascinating topic today, diving into the world of AI and ML and wireless communications technology with Tim from DeepSig. Tim, how are you?
Doing well. Nice to be with you here today.
Well, nice to chat with you. Really intrigued by the work you're doing as a former one time electrical engineering student and insider in the wireless industry for 30 years. Really exciting times. Before that, maybe introduce DeepSig and yourself.
Yeah, absolutely. So DeepSig is about 6 years old at this point, and we're a startup based in Arlington, Virginia, and we're really focused on leveraging everything that's happening in the greater machine learning world and kind of bringing that into some of the core wireless problems that have been problems for many years, but they're getting harder and harder to deal with and to solve. Um, and so really as we've seen deep learning transform vision and other fields, we've brought that into, how do you build wireless modems and baseband processing? How do you do spectrum sensing and spectrum awareness? And kind of some of those core DSP problems that, have been a challenge for the industry for many, many years.
Yeah, and enter AI and ML. What is the big idea behind DeepSig in terms of AI native wireless technology? What are you trying to solve for exactly?
So I think for many, many years, wireless has been this model driven problem.
Mm,
We build a statistical analytic model for the wireless world for how signals are transmitted and received. How we design the signals and transmit them. And I think one of the things that we've seen, with deep learning and with AlexNet in 2012, is that we can start making this transition from really heavily model driven systems to data driven systems. And so we can let machine learning optimize directly on all of the effects, as we see them over the air and in the real world. Um, and so, AI native kind of means in the wireless world, it's been used to mean, that you're designing an algorithm or a function natively with AI. So you're learning how to process data, from some end objective rather than, designing an algorithm as kind of a closed form expression based on some statistical solution, analytic solution, which is how it's been done for many, many years since the beginning of wireless, essentially. Um, so, this can be applied to a lot of aspects of wireless, how you process signals, how you receive signals in a base station, how you sense the signals around you in the spectrum. Um, so, yeah, there's a lot of different ways that these kind of AI native functions can enhance wireless systems today.
fantastic. And so I've been around, I'm not sure about you, but since zero G, actually paging, I started my career in the paging industry right through to one, two, three, four, 5G. So how do you see your technology shaping this evolution? What's next and what does your technology enable?
Yeah, so I think that the spectrum is becoming really, really congested, right? We have
Mm,
uh, a huge number of wireless systems now between our Bluetooth, our Wi-Fi, emergency
mm.
communications and radars and cellular signals and drone signals, satellite signals. There's just, we're surrounded by, so many different wireless systems. Um, and on top of that, you look at 5G, where you have massive MIMO, where you're trying
Mm.
to use these, very complex antenna systems to multiplex many, many users into the same spectrum, and dealing with, you know, orchestrating all of the different aspects of the spectrum. And you're trying to move to higher bands, to lower cost hardware. So you have
Mm.
just this increasing number of constraints that you need to optimize for. And so I think one of the big things as we move on to 6G and into the future wireless systems is how do we do all of this more efficiently? And how do we optimize for all of these different constraints together, with real world assumptions that aren't kind of a simplified model that you get out of a textbook? But I think those are some of the aspects that this can really attack. And ultimately, this is improving efficiency, coverage, bandwidth, reliability, and allowing you to really see everything that's going on in the spectrum so you can reason about it and optimize it effectively.
Fantastic. Well, speaking of textbooks, I have a few of those lying around. Gathering dust on traditional signal processing methods, DSP from back in the day. So, how do you differentiate versus those traditional approaches to real time wireless data transmission? And what is kind of unique about your architecture versus the way things have always been done?
Yeah, so I think if you look at how spectrum sensing has been done in the past, um, there's been kind of very non-sensitive energy-based systems that do energy
Hmm.
detection and these types of things, and then there's been very specialized systems that might be designed for one technology, or a couple technologies, and really moving to a data-driven approach makes this much more flexible. So you can rapidly retrain for all types of different emitters, as new technologies emerge, or as things like new types of interference and EMI are observed in networks. You can train for these sorts of things very quickly. So it makes it much more flexible, and it can be very cheap and efficient to deploy. As we've seen, kind of
Hmm.
all of the silicon vendors going this direction. Every silicon vendor is investing very heavily in efficient neural network inference, and so to some degree, it's riding this silicon trend as well.
Yeah,
Uh,
absolutely. Really exciting times. And there are many different approaches to spectrum sensing, different kinds of solutions and products and technologies. Your innovation is around spectrum awareness software. How do you see yourself fitting on that landscape, and how are you different from all the different approaches or products out there?
so today, if you look at the cellular example, um, monitoring for interference is really difficult. It's kind of a manual process. People look at network level KPIs. If you see throughput in a sector decreasing, you might need to send someone out with a spectrum analyzer to really sit there and do a manual process of looking for interference, hunting it down, figuring out what it is, and mitigating it. All of this we can start to automate. Um, you can kind of have this intelligence at the edge, so that your radio can figure out what's degrading it in a faster, more efficient way. Um, and yeah, and also we're seeing, many, many more autonomous platforms. So we have,
Mm,
automotive applications of wireless. We have, drones, both commercial and defense focused, that are all over the place. And awareness of the spectrum is becoming more difficult because there's just such a diversity of types of devices, uh, and also more critical, so that you can put this onto compact platforms, and have your platforms be able to respond and act intelligently rather than just interfering and talking all over each other, essentially.
yeah,
So we
huge
you know
issue.
yeah, so we build kind of the software core component that can be put out at the edge to provide this intelligence, and then everybody can kind of build smarter systems on top of this.
Fantastic. So we've seen with the rise of 5G, incredible use cases for low latency communications and mission critical applications, but we're still not near, almost near zero latency. How do we get there? How do you achieve the really incredible real time performance and optimize for ultra low latency kind of applications?
Yeah, so I think as machine learning has grown across many different industries, there's been an enormous amount of R&D put into how do you build very efficient inference models, or neural network inference. And so figuring out how to decrease the size of these models into to really compact, how to put them onto hardware platforms where they can have very, very low inference times, and how do you,
Mm,
quantize and fuse these different operations, so you can deploy them onto either DSPs or mobile GPUs, or ASICs or FPGA
mm.
devices. So we're really trying to take all of the R&D that's going on in this industry and bring it into how we deploy these models super efficiently for power and latency savings. And you
Yeah,
can really do a lot
really
of
exciting.
complexity reduction this way.
Right, right, absolutely. So I've had many guests on my show, so many applications and use cases from, agricultural technology to medicine and industrial Internet of Things. But what are you seeing? What are some of the industries use cases that are benefiting from your signal classification sort of tech? Do you have any examples you can share?
Yeah, definitely. I think all of these industries, certainly medical, you're seeing more and more cluttered wireless environments. Hospitals
Mm,
have so many wireless devices communicating over top of each other. So, definitely in IoT and telecom, rapidly diagnosing and deconflicting wireless technologies is a big use case, and diagnosing and mitigating any performance degradation. But there's also a major area around wireless security. So being able to understand when there's attacks going on at the physical layer in your networks, or if there's unauthorized drones or other uses in the area. Certain things like data centers really want to keep out unauthorized wireless devices that could pose
mm,
threats. Um, and so that's a big area. And then spectrum, really, we've always just kind of assigned different bands to different technologies, um, but that's been really pretty inefficient. So there's really a big use case for how do you just do a better and smarter job of allocating spectrum so that we have more capacity where certain applications are needed, and you're not wasting it on ones where you don't need them.
yeah, yeah, absolutely. And you mentioned so many these variety of applications. What are the other sort of pain points that you're seeing with customers as they deploy these low latency networks? What are some of the real world challenges, perhaps, that you see and the practical utility you can bring?
Yeah, I think in the RAN space, really helping to accelerate the diagnosis of interference, or uh, both from the same tower, from different bands, or from adjacent sectors, or from there's been a lot of instances of things like transformers or heaters, or even things like Bitcoin miners or headsets, just emitting EMI that can happen, you know, spuriously, or at hard to track times. And so being able to be monitoring that kind of continuously, so you have a view into what's going on in the spectrum that you can uh, you know act on and diagnose without a lot of resources, is pretty a new thing for the industry that they couldn't do before. But I think the biggest thing is really looking at things like 5G, where you have massive MIMO, where you just have so many degrees of freedom for how you do beamforming, how you multiplex the spectrum to more and more users at the same time, and how you do that in the context of really complicated propagation environments with lots of buildings and reflectors and blockage. It's a hard problem to do analytically, and by taking kind of this data-driven approach to it, you can really get capacity very quickly by letting it do this data-driven optimization for things like we're doing a lot of work in Open RAN, just to improve receiver sensitivity, so you get kind of extended range and coverage and capacity in the network. And as we scale up to more dense multi-user systems, this can really help push a lot more out of this. And this has kind of been a notoriously hard problem in 5G. It's like, how do you make the best use of all of these degrees of freedom in communication systems today? Tuning them and building these systems to operate near capacity is really a challenge.
Yeah, absolutely. Curious on a personal note, you spent a career in industry, in academia, amazing institutions like Virginia Polytech. You're an advisor to the FCC. How do you think about the industry coming together to solve these challenges? It's big challenges, but there's a lot of investment and work happening. It sounds like it's an exciting time for people like yourself, sitting
Yeah,
at the intersection of research and practical industry utility.
yeah, it definitely is. I mean, I think, and I started out more on the defense side before I went into the
Mm,
academic space and into the telecom space. And I think right now we're seeing a lot around things like CBRS, where you're sharing spectrum between federal users and commercial users, and new initiatives like the CBRS 2.0 that NTIA and FCC are leading. Um, and so there's a bigger drive to share spectrum more efficiently here.
mm.
And there's also a faster path from research, early research into applied research and commercial products than there's ever been. Um, I think everything is just accelerated so much in this space that it's a really exciting time to be able to focus on these topics that are, I think, really critical to all spectrum usage right now.
Yeah, and this is a global challenge, not just the US. What are some of the trends and challenges globally? And do you work with customers around the world as well as here in the US?
Yeah, we definitely do. We have two major Open RAN partners with
Mm.
HTC in Taiwan and Viettel in Vietnam,
Oh,
and
wow.
there's been a big push to build Open RAN based RAN systems so that you can have um, virtualization of your base station components, and you can maybe domestically build a number of the components like the radio units and different aspects of the stack. And so there's a massive demand now for, as you virtualize all of these components, how can you really make them performant and state of the art uh, in spectrum performance? So I think this is kind of a massive demand area that we're really focused on serving as we work with different partners and OEMs to bring these capabilities to market.
It sounds like you have a multimodal business model working with partners and customers, perhaps telcos. That must be pretty exciting, rewarding to have such an interesting bird's eye view of the industry.
Yeah, absolutely. It's really awesome to be able to work with different partners across kind of the sensing and the RAN
Mm,
landscape to really be able to deploy some of these components into operational and deployed systems where you get the data and the ability to test these data driven approaches kind of in very harsh urban environments where they can really add the most value.
absolutely. What's next for AI and signal classification? What do you think is on your radar or roadmap, both from a industry standpoint, maybe academic standpoint, or even regulatory standpoint from folks like the FCC and other bodies?
I think we're seeing a lot more interest in using it more broadly. I mean, it's always been fairly expensive and specialized, and not super practical. We haven't had the ability to deploy sensing pervasively throughout wireless networks before.
Mm,
But I think just because of silicon trends and these kind of algorithmic trends, it's now becoming super practical to put sensing into many different network elements. And so this is just something that's never been possible. And now we can do a much better job of deconflicting interference and allocating spectrum more efficiently and improving kind of receiver and end-to-end performance. I think we're also seeing a lot of discussion in the context of next generation, both for 5G advanced and for 6G, in terms
mm.
of where aspects of this can be brought into the standards to really help drive performance. So things like rather than sending channel state information from a phone back to the base station, you can learn an embedding that more efficiently and compactly feeds that back. And so this can reduce overhead, and it can give you kind of better better MIMO and better beam control in
Mm.
a lot of these systems. And I think
Well,
ultimately,
who couldn't want that? That is super exciting. Yeah.
and there's this concept now of an AI native air interface where rather than using things like QAM and fixed framing and pilots to transmit
Mm.
information, you can let it learn kind of the entire modulation and physical layer and structure to transmit information more efficiently. And so this, I think, is a really exciting concept, that may find its way into 6G. And for things like, FR3 and these 10 gigahertz or higher, centimeter bands, it can really help cope with different types of channel and propagation effects that are difficult to cope with. Um, and to do that in a closed form way is can be very computationally and suboptimally in terms of when you deploy it in the real world. So I think there's a pretty exciting opportunity here as the industry and the standards are all kind of starting to move this direction to try to leverage machine learning at the lower layers of the stack.
Well, fantastic opportunity. Congratulations on all the good work. How can people reach out to you or the team to get involved or collaborate? Are there industry meetings or events that you guys attend? Or I guess they can just go to the website, right?
Yeah, absolutely. We're at deepsig.ai. You can reach out to us there or over email or Twitter. We're also at a handful of industry events. Often, some of the major Open RAN
Hmm.
events will be at Mobile World Congress again. I think this in the U.S. and the main one this next year.
Great.
Um,
Well, I'll see you there. That would be great.
yeah, we'd love to meet up there. And
Fantastic. Well,
we're always looking for new partners and OEMs
hmm,
that have a need for this because I think as the industry starts to look at how to adopt these, it's a bit of a shock for a lot of modem and radio designers to start rapidly leveraging machine learning, which is
hmm.
an incredibly deep and complex field in addition to telecoms. So bringing those together is can be challenging, um, and that's kind of really our specialty is focusing on that intersection and having components that can get people going and benefiting from it very quickly.
Wow, fantastic. Well, challenges, opportunities, disruption ahead. Thanks so much for sharing your vision and mission at DeepSig. Really exciting. Great work. Onwards and upwards. Thanks, Tim.
No, thank you. Thanks for having me.
Take care. Thanks, everyone. Bye bye.